Alright, welcome to this talk about the argmax constraint. I'm Peter Stuckey and this is joint work with Graeme Gange. So what is the argmax constraint and why is it important? So the argmax constraint we use is this example here. Z is the argmax of x1 to xn. And what is meant to mean is that Z is the index of the first position where the x variable takes the maximum value. And that first position is important because it makes it a function, and particularly for the first usage of argmax, which we'll talk about now, which is in encoding conditionals. So if you have this big conditional expression, if b1 then e1, else if b2 then e2, blah blah blah, then you can actually encode that with argmax. So basically we're looking for the argmax of this Boolean list. The max will be true because the last element is true, that's the else branch. And so we'll find the index position of the first Boolean which is true. Then we use that to look up in the array of expressions the one that we mean to assign to x. So that's a very neat usage of argmax. An increasing use of argmax is because it appears typically in the last layer of some kind of classification machine learning model. So you have these scores, S1 to Sn, which are the score for each class I, and then you say C equals argmax of this, which gives you the class which has the maximum score. And that's typical in many machine learning models for classification. And in general, argmax allows you to embed an optimization problem as a subproblem and make use of its best answer. So max just gives you the maximum value that you can get out of the subproblem, but argmax allows you to understand which instance was the max and which was better. So what's wrong now? Well, there's no argmax propagator that we're aware of, and the current default implementation in Int'l is not domain consistent. So what have we done? We've built a domain consistent propagator and made an incremental one. In fact, it's easy to make it incremental. We've also found a new domain consistent decomposition which works for integers, and we show that the new propagation and the decomposition are better. And what surprised us was the decomposition actually beats the propagator in learning solvers in many cases. So just some quick results. So on unit tests we can get 2 orders of magnitude improvement over the existing decomposition in some wireless signal selection where you use argmax to work out which tower a handset is connected to. With argmax you can get an order of magnitude improvement, and if we're doing minimal explanation of some boosted tree models and we want to use this, that the actual model only has one argmax in it in a very large model, but we can still see a noticeable improvement by using either of the new methods. So in conclusion, we've implemented an argmax propagator for our solver. Well, you should go and implement an argmax propagator for your solver. If you're using Minizinc, you'll already be using the new decomposition. It was already included in earlier releases, and it allows CP to reason better about ML models. All right, let's continue with the longer talk. We're going to introduce some notation. We've got domain, and d of x is the current domain of the variable x, and we can take the lower bound and the upper bound of that. We're going to talk about atomic constraints, which is a way of representing parts of the domain. So x equals d, that's the atomic constraint, which says that x can only take the value d. X greater than equal to d means it has to be a value greater than equal to d. Strictly greater than d, which for the integers is just greater than equal to d plus 1, for reals is different. Less than or equal to d, which again for the reals is different. For the integers we can use a negation of a greater than equal to d plus 1. And some shorthands, not equals and less than as well. We're going to introduce this weird notation for reasoning about argmax. So this is x double arrow b y, and you can think of b as a Boolean which indicates the strictness. So if b equals 0, this is saying x is greater than equal to y. If b equals 1, it's saying x is greater than y. For integers, this is the same as x is greater than equal to y plus b. You can define the other direction similarly. And why is this important? Because if we take 2 of these xi and xj's in our argmax constraint, if we have xi is less than I less than j xj, it means it can't be the argmax. So either it's in an earlier position and it's strictly less than xj, or it's in a later position and it's no more than xj. So in neither case can it be the argmax. All right, so let's look at the current decomposition. So we introduce these auxiliary variables mi, which keeps track of the max that we've seen in the array so far, and pi, which is the position of the max we've seen in the array so far. Obviously at the beginning, M1 is just X1 and P1 is just 1, and then we can update them. So Mi plus 1 is just taking the max of the previous max plus Xi plus 1, and the position update is the interesting part. So if the previous max is strictly less than what we see in the current position, then the I plus 1, that position is the new max. Otherwise, it's the previous position. And then Z, the argmax, is just the position we found by the end of the array. Okay, so there's some problems with this. If we look at this example of an argmax over 4 variables, we note that Z can't take the second value. It's not allowed to. If we work out the domains of the Mi and the Pi variables, we have them there, and we don't infer anything, even though we'd like to infer that Z is not equal to 1, because you can see that the minimum possible value of the max is 4, and Z1 can only take the value 1 to 3. We also like to infer that x2 is less than or equal to 5, because imagine if we set x2 to 6, then you can see that no other variable could be the argmax. So x2 would be forced to be the argmax, but we know that x2 is not the argmax because Z doesn't have 2 in its domain. So the current decomposition is very weak. What can we do about it? Let's look at what is the possible things that argmax could ever propagate. So there's 3 rules. Here's the first one. It's a bit of a wall of a text, and mainly because of this difficulty about positioning and arguments. So if J is known not to be the argmax, then it can't take a value greater than the maximum possible value of the remaining xi's, which could be the argmax. So here we work out the position, UBI, of the argmax of the upper bounds of all the variables which are still in the domain of Z. And UB is the value that it takes at its upper bound. And we have this constraint. If Z is not equal to J, so we know that Z cannot take the value J, then Xj has to be less than, if J is less than UB, the UB. So that means if J is smaller than UBI, it has to be strictly less than the UB. If J is after the UB, the position of the upper bound, it can be equal to. Right? So if we look at our example, the position of the index of the current upper bound is argument index 4, which take the value 6. And because of Z not equal to 2, we get this implication that x2, which is not in Z, is strictly less than 6. Right? So it can't take the value 6, and has to be less than 5, less than or equal to 5, which is exactly one of the missing implications we had. The second rule, so if we know that the maximum possible value of this index position is less than the least possible maximum value of the other xi's, then it can't be the argmax position. So if we work out the index of the argmax of the lower bounds of all the variables, then if we see that xj is less than this lower bound, and this is this, again, funny less than, if j is earlier in the result, it has to be strictly less than. If it's later, it can be up to equal to. Then in none of those cases could it be the argmax position, and so we can set Z is not equal to j. So if you think about our example, the position where the argmax lower bound was maximum was, again, position 4, its lower bound was 4. Because we can show that x1 is double less than 1 less than 4, 1 less than 4, 4, which is the same as saying x1 is less than 4, that implies that Z is not equal to 1. So we can get that missing implication. Let's look at the third rule. So this is the least applicable rule. Basically, if we know the argmax positions, or Z is known to be J, then that position can't take a value which is too low. So if we look at the lower bound across all of the x variables, then we know that this position, which has got to be the max, has to be at least as big as that. And so that's, if Z equals J, then we can make this assumption. So if we take our example, just modify it slightly by making the domain of Z equal to 1, then we still have the same LBI is the 4th index position, and lower bound was 4, and because Z equals 1, we get this x1 strict 1 less than 4. In this case, it's 1 less than 4 is false, 1 greater than 4 is false, so we get x1 is greater than or equal to 4, and we can infer that, but that fails, of course, because the domain of x1 is 1 to 3. All right. We can prove that if you apply these rules exhaustively, that enforces domain consistency. So let's build an argmax propagator. Well, actually, you can do it fairly straightforwardly by implementing the rules themselves. And indeed, an incremental version of the propagator is also straightforward because each of the rules essentially is an incremental implication. So here, basically, you can see the first 4 lines implement rule 1, the second 5 lines implement, the next 5 lines implement rule 2, and the last line implements rule 3. But we need more than that if we're using a propagator in a learning solver. We need to be able to explain each of the propagations. And mostly these are straightforward. Rule 1 is the most involved because we have to explain where we got this UBI, as in this position of the index position of the current upper bound. And to do that, we basically have to show that, well, for all of the k's, all of the positions that are in the domain of z, they can't be bigger than that upper bound. And for all of the k's that are not in the domain of z, well, the z is not equal to j. So we have to remember the ones which weren't there, because if we didn't, they could have changed the upper bound. And if we get that, then that's enough to enforce the right-hand side. So rule 2 and 3 is much more straightforward because basically the LBI index, the index where we find this maximum of the lower bounds, is enough to explain it. So if we know that at the position LBI we have a value greater than LB, that together with the fact that xj can't be bigger than that forces that z can't take the value j. And rule 3 is again straightforward. The first literal looks a bit complicated. This is just to make it work correctly for reals, where we can't just invert things. But in the integer case, it's exactly the same as saying x LBI is going to LB. All right, so we were very happy with our wonderful propagator, incremental, domain consistent, and then we stumbled on this idea. So we can actually do a different kind of decomposition. So we can think about argmax as the lexicographic max of these pairs. So xj, so that's the variables, the value, so that's the most important. And then n minus j is basically an inverse of the position. So we're favouring early positions over later positions. And so hopefully you can see how if we order those things in lexicographic order, the lexicographic max of those actually gives us both the value of xj and its position as this pair. So for integers we can encode this. Right, so we have qj which encodes this pair of xj of n minus j, and m which is the maximum of these qj's. So the constraints to do this, well, we just have this qj which is n times xj plus n minus j, so that just encodes the pair as a single integer. M is just the max, the normal max constraint over the q's. And then the real work is done by this last thing, which says that z is not equal to j if and only if m is greater than qj. So basically, if you're not the maximum position, then you can't be the argmax. And this works because qi is less than qj if and only exactly this xi less than equal to I less than j xj thing that we added in. So let's have a look what happens on our example when we use this decomposition. So we work out the domains of the qi's. Actually, they'd be individual elements. Here I'm only going to look at the upper bounds and lower bounds. And we can see immediately, so m's lower bound is 16, which comes from position 4, and since m is bigger than q1, we know that already because its upper bound is 15, we can immediately infer z is not equal to 1. So that's nice. And for the second one, it's a bit more complicated. Okay, from z is not equal to 2, we infer that m is greater than q2. Now that means that q2 has to be less than 42, because that's the value that m's maximum value. Once we do that, we get that x2 is less than 9, and then we get that q2 is less than or equal to 38, because q2 is just a function of x2. And now we get that m is less than or equal to 38, because in fact it was q2 which was giving us the maximum value. But now that forces q to be to strictly less than 38, so x2 is less than or equal to 8, q2 is less than or equal to 34, m is less than or equal to 34, etc. And this goes on and on and on until eventually we find q2 is less than 28, and we find that x2 is less than or equal to 5, which is exactly what we're hoping. And this is when basically this q2 can no longer be giving the max. The max will be going to q4 at this point. So we can show that this enforces domain consistency under the assumption that we have domain consistent propagation of these qj equals n times xj plus n minus j constraints, and just bounds consistent propagation of the max and the inequalities, which is basically the propagation that we use for those things anyway. And note that this qj constraint is really a binary constraint, and it can be implemented by view. So we can introduce these qj variables essentially with no cost to the solver. And that makes this decomposition quite attractive. The size of the decomposition is order n. We just have this one max constraint, n of these views divided into qj, and then n reified inequalities for these bj if m is greater than qj, and then clauses to equate the bj with the booleans that represent the z variable. So let's have a look at some experiments. So the unit tests, so here we've just got a model with n copies of argmax and a single all different constraint and nothing else. And basically we just, we take some random numbers times each xj, and we take the argmax of each of those arrays. And the chances that this all works, that we actually make sure that the argmax is each in a different position and they all agree with each other, is basically unlikely, vanishingly unlikely, and we check that it doesn't occur in experiments. So what we've built here is a small problem which has no solution. And that's good because it forces the solver to do a lot of backtracking, a lot of search, and you really work out your argmax propagator. And what we can see is the old decomposition deck is very, very bad compared to the new one. So here the propagator is really the best, very, very fast, 2 orders of magnitude faster than the old decomposition. And the new decomposition is surprisingly good. It's about twice as slow on this example. So let's have a look at a more realistic example. So here we've got clients that are connected to access points, and they're connected to the one with the biggest signal strength. And the client has a desired throughput and the access point has throughput limits. And then we're trying to assign signal strengths to the access points to make sure that the clients who end up being pointed at them fit within the throughput limits. And so we've run these examples 10 times, and we've got the average time with the 600-second timer included. You can see the number of times it succeeded in the brackets there. And here we see again that the propagator, the new propagator, is an order of magnitude, well, sometimes, yeah, it's kind of an order of magnitude better than the old decomposition. At least you can see that clearly for the cases where they both solved 10 examples. But the new decomposition is actually somewhat stronger, kind of twice as good. And this is because the qj variables actually help in learning, and the n variable help in the learning, and so we can actually learn more succinct and more reusable notebooks. For boosted trees, here we've got a boosted tree model, XGBoost, and we've got an instance which has been given a class label, and we want to derive the cardinality minimal explanation. So what the smallest part of that instance which will force that class label. So this is a large model, but it only has one argmax constraint. Most of the model is many elements and linears. We looked at 2 example cases here, and you can see that the old propagator makes a significant difference, even though there's only one argmax constraint in the entire thing. Okay, much more difference in the chess example than the soybean, but you can still see a notable difference. The difference between the propagator and the new, they're almost equivalent on these examples. So, to conclude, what have we done? Well, we've built a domain-consistent propagator for argmax, for works for both integers and reals, and a new domain-consistent decomposition for argmax for integers. And we can see much improved results over the original decomposition. And one thing we'd like to point out is argmax is really important if we want to use CP for explainable AI. And I think that's an important area that CP should be looking for application. Thank you.